Okay, first it is assumed that the model's main element are point objects moving with a constant velocity in a three-dimensional space. I'll draw two dimensions x, y here. Actually, I'm going to label this v sub x and v sub y. And we are saying that the v sub x and v sub y is between plus c and negative c, plus c and negative c. And so basically v sub x squared plus v sub y squared plus v sub z squared is less than c squared. That is the vector velocities v from a set. This would be basically described as b of 1, the unit ball b of 1. R is in R3. R is in basically v sub x, v sub y, v sub z. R is less than 1. R is basically the v is less than c. Every element v in that volume represents exactly one object. So so that means, for instance, we could describe a v sub x, comma v sub y, comma v sub z that is from a set that is in the unit ball, but it doesn't, that I might not necessarily be in the set v. So we might have an infinite number of velocities that are in the set v, but you might still be able to pick out a set of velocities that are not in b, or that are not in v. So b is a continuous set, the unit ball. V is probably a set of discrete points in the unit ball. So let's go on. The bound 1 corresponds to the speed of light, c squared, and I'll erase so that I can continue. All objects is started at a common instant t equals 0. Let's do a spacetime diagram real quick. X and t. All objects did start at a common origin, t equals 0, at the origin of the space coordinates. So v equals ct would be the outer bound of this thing. I'm sorry, r equals ct, and r equals negative ct over on the other side. So we're imagining all of the particles with their respective velocities, r equals vt, going out. That means that to a single object with a velocity v, it is additionally assigned to the world line r equals tv. R equals tv, which is an abbreviate notion of the set L sub v equals t, comma, r. Wait, L sub v equals t, comma, r, member of R13. I think this L sub v is a world line. L sub v is the locus of points t, comma, r, such that r equals tv, and v is a vector, t is a vector, because t is r1, r is r3. So we're going to be multiplying r is t times v, so it's time times meters per second. V is in v, so that's that discrete set of velocities in the unit ball, limited by the speed of light. The state of the universe at instant t, and this is, I think, in cosmological time. And this is by definition, it's a definition. I really feel like a definition should include both the words instant is not, well, because V was selected from a discontinuous set, instant T, the instant T is composed of a discontinuous set of events. It's not exactly, I mean, it does follow this shape, but those events are not the age of the universe. They're a discontinuous set of events that represent each of those discrete particles reaching that moment. Now, it does form an approximately smooth curve, yes, but this is a by definition sort of thing. And really, it should be particles of the universe at instant t rather than the universe at instant t, because the universe itself has an observer-dependent age. Because the universe itself, I would think you would use this t equals constant line. If you were going to say there was an instant, you wouldn't use those things there. But I'm going to go ahead and use this for now, because we want to say he's giving the events of velocity v at instant t. So that's refers to the Hubble particle of v, of velocity v, the Hubble flow particle with velocity v, and its clock at time t. And it's going to be described by, and this is an event, t comma r sub v, t sub v comma r sub v, is a member of L sub v, which is those world lines, worldline events. Worldline, those are, okay, L sub v is basically, because v was a set of discrete velocities, L sub v is a set of discrete world lines. And so these are events that are attached to those discrete world lines. And then we have our such that t sub v squared minus the length r sub v squared equals t squared. So essentially we are attaching that to a hyperbolic arc in the space-time. So these hyperbolic arcs, if we have t going this way and r going this way, absolute value of r going this way, then each of those hyperbolic curves marks out, and those are gonna go all the way. Each of those hyperbolic curves are going to be associated with a value of t, and if we have something going velocity v, then all of these points, let's see, the universe at instant t would be described by one of those hyperbolic arcs in Euclidean space, and t being, we need a name for that t. Actually, let's jump ahead a little bit so we can name it. We've got fix an object indicated by the velocity is 0, 0, 0. That is this observer right here. So t, this little t, is observer coordinate time. We're calling it observer. He's the stationary observer. So little t is observer coordinate time. He goes on to say, this implies that the universe at instant t is contained in the hyperboloid h sub capital T equals t squared equals the set t squared minus r squared equals capital T squared. So I think, I'm not sure why he uses implies. It seems almost a repetition of what he said here. T sub v squared minus. Oh, no, it is different. Okay, because these are discrete elements. H sub t is an actual surface. E of t is a collection of discrete events. H sub t is a surface in that is a continuous surface in the spacetime. E of t is a set of discrete events. So that is a difference. Okay, now let us fix an object by our velocity v sub naught equals 0, and let us call it an observer. And the rest of this note is a list of strict formulas without approximations, which relate the observed redshift z of, okay, let me draw a couple of points in here and a line and here, and we'll just draw another line there, and then we'll draw a parabolic arc through here. Let's call that tau. This is the instant tau, and then up here we'll have the instant t, and down here we'll have maybe a little t. And I think this diagram kind of represents what it is. We're going to have an object fixed by velocity v sub naught equals 0. So that's r equals 0t. That's what that one guy represents here. And we're going to have this observed object over here that is moving with r equals vt. And v here is the absolute value of the velocity v of the observed object. T comma r is the event of the emission of the light from the object over here, absorbed by the observer at instant t. So that's why this is capital T up here. This is where it is absorbed by the observer at instant t, where r equals r. So this distance here is the Euclidean distance of the observed object from the observer at the instant of that event. Tau, which is this instant here, tau is the proper time of the observed object at the event of the emission. So that is how much this object has aged along its path here. So that is the tau is the proper time of the observed object at the event of emission. Now the equations. Tau squared equals t squared minus r squared. And you can see that here we got t and r, and in hyperbolic coordinates, tau is how much an object ages, would be square root of t squared minus r squared. How much the object would age from this event to this event if it traveled along a straight line. You can see here t, this is distance r, and so if r equals ct, then this slope is like basically a 45-degree line for the light traveling from here to here. So this time t equals r plus t, because this is also going to be r. It's a right triangle and hasn't been drawn to scale, but this would be 45 degrees and this would be 45 degrees. So t equals r plus t. Then the velocity is the slope of this line here, and it is the distance traveled divided by, t, this value here. So next comes a kind of surprising calculation of the redshift. So the redshift here, he's saying that the redshift observed at this point is going to be equal to the amount of time that has passed for this guy at this event compared to the amount of time that has passed for this guy at this event. It doesn't show his reasoning here, but I think it seems good, and besides, I already know that this is actually exactly what's called the relativistic redshift equation, so I have no reason to doubt. So yeah, I think this would come out accurately. I'm gonna go ahead and put it. I'm too lazy to do the math myself, but I'll plug it into Mathematica and see if I can get that result real quick. So I'm plugging in tau equals t square root of t squared minus r squared, and big T is just r plus t, and r is, little r is v times t, and then I tell Mathematica to calculate square root of tau over t. It gives me this square root of t squared minus v squared t squared over t plus vt. So let's simplify that a little bit, and we'll have t times the square root of 1 minus v squared divided by t times 1 plus v, which comes out to be t times the square root of 1 minus v times 1 plus v divided by 1 plus v. I'm sorry, t over t cancels, so we just have that, and then we could take this divided by the square root. Let's multiply 1 over square root of 1 plus v, 1 over square root of 1 plus v, and we have square root of 1 minus v divided by 1 plus v. All right, so we seem to have this definitely represents the relativistic redshift. Rho, though, what is rho? He's defining rho to be this distance here divided by this time here. What does that signify? Well, it seems sort of a perceived velocity. What? Yeah, it's the distance to the image divided by the age of the universe at the time of the observation. So I'll go ahead and stick that one in here too, r divided by t, and see what pops up. And basically what came out of r over t was v over 1 plus v, which he had 1/2 1 minus alpha squared, which would be 1 minus v over 1 plus v, 1 squared, which would be, no, I already squared it, 1 minus v over 1 plus v, which would be 1/2 times 1 plus v over 1 plus v minus 1 minus v over 1 plus v, which would be 1 minus 1 is 0, v minus negative v would be 2v over 1 plus v, taken to 1/2 would indeed be v over 1 plus v. So yeah, it comes out the same. All right, so we're getting towards the 20-minute point in the video. I'm gonna just go ahead and finish up here, or say thanks for watching right now, and come back to this in another video.